This class will be dedicated to, let's say, most practical issues which we believe are needed for you to jumpstart your project, your coding project. Alice knows already this paper, which paper, but let me first go up. This paper is fast Jerry synchrotron codes, and Alice and Jason has completed most of the coding within this algorithm without one important thing, from which I will start actually. So the idea behind this fast codes is that some mathematical expression can be computed much faster within some approximation than if it is computed in its exact form. And the approximation behind that is that one of the integrand, one of the expressions which has to be integrated over may be approximated with a Gaussian, analytical Gaussian function with really very high accuracy. And this figure shows you examples of it. So exact value is dashed line, exact computed from numerical computation, and you see that Gaussian fit is very, very closely matched. Gaussian fit, which is solid line. And now, what Alice has done a year ago, she considered one case of isotropic distribution of radiating particles, and this example is shown here. And for isotropic particles, the peak value of the Gaussian can be found analytically approximately, and this is this value mu naught pk. pk means Petrosian-Klein, under names of scientists who found this value first. You can see that it's not exact, it's clearly deviates from actual peak value, but it's not far away from it. But for isotropic cases, it's sufficiently close to the peak value to be used in practice. And this is, again, the case of the quad which has been built last summer. Frequently, particle angular distributions of radiating particles are not isotropic, so they have preferential direction of their motion, maybe along the magnetic field or transverse to magnetic field. And in this case, we have a real issue with analytical approximation. You see that actual value is somewhere here, and approximate is somewhere there. Or in other case, correct value is here, analytical is there. So such cases, if we use analytical value for such cases, we get large errors. We do not get correct answer. So what will be one of your assignments? One of your assignments will be to make a code which would efficiently find numerically this mu naught value for arbitrary case, isotropic or anisotropic. And this paper just explicitly tells you what exactly must be coded. And this is related to this H function. Many ingredients has been already coded by Alice, so you will use some blocks, and eventually we have to solve equation H prime over mu equals to 0 And the root of this equation gives us the desired value of mu naught. Again, this is the visual difference between mu naught and mu naught analytical. In terms of this equation, what happened last year, we neglected, in this equation, we neglected this term, and we neglected this term, and we neglected this term, and after that, the equation reduced to just this combination equal to 0, and this mu is analytical mu naught pk, where mu naught pk equal n beta time cos theta. So the simple analytical solution which is implemented now. So next step would be to consider full equation. For full equation, a lot more complexity comes into play, and Dr. Nita has some preliminary programs which could help you to solve such equation, but he has a piece of code in very general way in which nothing of this input is implemented. By implementing just general solution, general algorithm of finding this solution in array efficient fashion. More or less straightforwardly to extend this, but it's not straightforwardly easy to do, especially when our requirement is to avoid do loops as much as possible. If at all possible, you should not use any do loops in your code. This approach will make your final code as fast as possible. Now, the second sub project, or the second piece where improvement is needed, we basically discussed during previous class. We need to implement the radiation transfer, and in terms of radiation transfer, if I will have time at the end of the class, I will probably show some pieces of code, but in fact, I believe that it's much simpler task, because you just have to move from, is it this one? Yeah, you just move from one voxel to the other one, and you account for new emission and absorption of incident emission, and just do it carefully, account carefully for such cases, again using known formulas, and you are done with your radiation transfer. Just a matter of applying the radiation transfer carefully from using transition from one voxel to the next. And what else is needed? A third sub-project is it's another part of the same paper where these fast codes were introduced and presented. The other very important ingredient is ability to account for many different distributions of thermal and non-thermal electrons over energy and pitch angles. So the distribution, again, non-isotropic in the general case, and if we simplify the case, we consider that distribution of electrons as a function of energy and pitch and cosine of pitch angle can be presented as a product of two independent functions. One of them is function of energy, and the other one is just function of angle of cosine of pitch angle. And again, last summer, only one distribution over energy was implemented, and one distribution over angle. Distribution over angle was just constant, which means particles were isotropic in the existing implementation, and in terms of distribution function over energy, only one single case of power law distribution like this one was implemented. So power law distribution in the log-log scale looks like straight lines. The bigger the spectral index, the steeper the slope. And in this case, for example, this power law is valid between 100 keV and extends up to 10 MeV. keV is kilo electron volt, MeV is mega electron volt, so it's just 2 orders of magnitude. So in this document, you can see different cases. This is Maxwellian distribution, and to the right you see sample radiation spectra from Maxwellian distributions. And for the case of power law, you see sample spectra from this. This spectrum of electrons produces this sort of radiation spectrum. This one corresponds to this one, and not surprisingly, dotted one corresponds to dotted one. So only this one implemented, but in fact we have a need to implement many more of them. And all the distributions which are needed to be implemented are described here, I believe in detail sufficient for you to quote the corresponding distribution. For example, this is the case of thermal distribution, and I believe and I hope that all relevant parameters are defined in the text. If they are not, you ask me, and likely I will explain what is it. So we have thermal distribution, and each distribution has its own index to be distinguished in the code, and to be distinguished when the code is being called by the user. Thermal to be implemented, single power law distribution has been implemented, not to be modified, so it's fine. Next one is double power law distribution of the energy, which is something like that, which has break up or break down. Again, you can see how radiation spectra look like. Power law. So-called thermal non-thermal distribution, when thermal core is linked with the power law. Somehow different kappa distribution. Here's the equation for it. What else? We can implement power law distribution over various variables, over energy, momentum, or Lorentz factor. All these are a little bit different from each other. And our Lorentz factor, thermal, non-thermal distribution over momentum, and thermal, non-thermal distribution of Lorentz factor, and couple more. Couple more are not here yet, but there are two more distributions which has to be implemented. We added them later, and I will just inform you about what they are at a later point while you are here. Basically, they are a combination from single or double power law and just Maxwellian core, without particular matching between these two. And the other piece of similar work is coding of distributions of pitch angle. Again, all needed distributions are listed here and explained how they work. So isotropic is constant, and the fact that 1 over 2, which comes from normalization of the angular distribution function, exponential loss cone, which behaves like that, and the Gaussian loss cone, and this picture how they behave. This is exponential loss cone, this is Gaussian loss cone. What does it mean, loss cone? That means that here you have particles transverse to magnetic field, which can be trapped in the magnetic field. But particles with pitch angles closer to the magnetic field direction can leave the magnetic trap, and you can have lack of electrons closer and closer to the magnetic field direction. And this effect is called loss cone, because electrons are being lost within a given cone of angles. And how exactly the electron distribution falls within loss cone can be described by different functions. It can be just sharp, can be exponential, can be Gaussian, can be something else. And we have, I believe, five different angular distribution to be ordered, and in particular Gaussian, like described here, and like corrupted Gaussian, where another term to the power of 4 is added to the index, which is right here, which we call super Gaussian, just deviation from the Gaussian. So the idea is to carefully go from one by one, and make the codes for all these functions, and create a mechanism how the code will distinguish which distribution function to use depending on input parameters. The dependence on input parameters are generally described in another document, in online documentation about polling conventions, and this is general polling convention, how we work with just single uniform volume. But I believe that Dr. Nita will tell you in more detail how this is realized in practice on the JX Simulator platform. And at this point, I stop this part of my presentation, and again